going back to what I was saying in the very beginning. Sorry about that, guys.
Nice to meet y'all.
What I was saying in the very beginning is, given this definition for an increasing and decreasing function, we can find that the derivative of our function will tell us whether or not it's increasing or decreasing. First, if the derivative is greater than 0, our function must be increasing. If the derivative is less than 0, our function must be decreasing, and if our derivative is equal to 0, it must be that our function is constant. Then, looking at this example, we've got x squared. Well, graphing it really quickly, we can see that for every x value less than 0, our function is decreasing. For every x value greater than 0, our function is increasing. So we expect that our derivative for x less than 0 will be negative, and for x greater than 0 will be positive. When we take the derivative, we graph it, we can see that that's exactly what happens here, right? So, since the derivative of our function is equal to 2x, for every negative value of x, we're going to get a negative derivative, right? And for every positive value of x, we're going to get a positive derivative. So from that, we get that we are increasing for any x value greater than 0 and decreasing for any x value less than 0. Now jumping back to this problem, what we've got here is a consumption rate, or a consumption function. It's just kind of fun to say, consumption function. We've got a consumption function equal to negative 0.0333 t squared plus 0.996 t plus 5.4, and it's in the interval 7 and 14 inclusive. And what we want to find out is if this is increasing and where it's increasing. So we're going to take the derivative. We're going to show that the derivative, whenever t is 7 or greater, is increasing, right? So we take the derivative. And we can see that for any value 7 or greater, this thing is increasing, right? Having said that, a natural question to ask then is, what about when the derivative is equal to 0? We call these points critical points, or critical numbers. And notice, whenever the function has a derivative that's equal to 0, or is undefined, we either have a cusp, an asymptote, or we're moving from an increasing to a decreasing, or some combination of all of those two, right? Make sense what I mean? So, definition of a critical number is any number c such that the derivative of your function at c is equal to 0. Which brings us to a nice convenient test for figuring out where functions are increasing and decreasing. Sticking with this x squared example for just a second, we know the derivative is equal to 2x. Setting this thing equal to 0 tells us x is equal to 0, right? So if we create a table of values, this is going to be every x less than 0. This column is going to be every x greater than 0. All right. Now what we're going to do is over here, we're going to pick a test point. Let me use a different color. Interval, test point, evaluation, and conclusion. All right, we're going to choose a test point here less than 0. Let's choose -1. Here, let's choose x is equal to 1. We're going to evaluate our derivative at -1. It's going to come out to be -2, right? So we can conclude that this must be decreasing, right? Evaluating our derivative at 1, it's going to give us 2. So it's positive, and we can conclude that our function must be increasing. So what we're doing here is we're first taking the derivative of our function. We're determining what the critical numbers are. And then we're partitioning our number line using those critical numbers, right? In our example case, we only have one critical number, so we only have 2 intervals to concern ourselves with, right? From there, we're choosing a test value inside of our interval. We're evaluating our derivative. We're applying the test, and we're making our conclusions from that. So I'll give you all 2 minutes to try this as an example on your own really quick. So what do we think? What's going on with this? In our interval from negative infinity to 0, is our function increasing or decreasing?
Decreasing.
I'm sorry.
Decreasing.
Increasing?
Decreasing.
Decreasing. All right. We think it's decreasing. So let's check it. Let's use a test number, -1. Throw that test value into a derivative. This is going to come out to be -3 times -2 or 6, right? So it's going to be increasing according to our test, right? Yeah. In the case of using a test point of 1/2 for our interval from 0 to 1, well, we're going to have 3/2 times -1/2. It's going to come out to be -3/4, right? So here, it's going to be decreasing in this interval. And 3 times 2 is 6. 2 minus 1 is 1. 6 times 1 is a positive value. So this is going to be increasing, right? Is everybody with me? So the graph of our function here we can kind of break it up into 3 different parts. All right, so this is the part x is equal to 0. This is x equal to 1. We know through here, our function is increasing. Through here, it's decreasing. And through here, it's increasing. So we can start kind of maybe piecing together what our function's going to look like, right? Check it out, looking at our function itself, it's increasing for every value of x less than 0. For every value of x between 0 and 1, it's decreasing. And for every value of x greater than 1, it's increasing. Just like what we've got up here on the board. So comparing methods. They chose same test values. Checking the sign of the test values, they determined that we're increasing, decreasing, increasing. And to determine how to break up these intervals, they set their derivative equal to 0 and found the critical numbers, right? 0 and 1. They said everything to the left of 0 is its own interval. Everything between 0 and 1 is its own interval. Everything to the right of 1 is its own interval. Yep. All right. Here, as an example, we've got this crazy function. Notice what we've got down here are cusps. So we know if we're just going to be going off of the graph of the function, we know that we're going to have non-zero, or well, we know that the derivative at these 2 points won't exist. That's what I'm trying to say. Make sense? So taking our function, applying the derivative, we get this crazy rational function. We solve for when our function is equal to 0. That gives us x is equal to 0. And then we solve for when it doesn't exist, when there is no value for our function. It gives us -2 and 2. So here, we're going to break our interval up into all the numbers of x, or all the values of x less than -2, all of them between -2 and 0, all of them between 0 and 2, then all of them greater than 2. So we're going to have 4 intervals. Choosing test values, we're going to compare if our derivative at that test value is less than or greater than 0. We're going to find that we're decreasing, increasing, decreasing, increasing. Decreasing, increasing, decreasing, right? This is all pretty much straightforward, right? Like there's nothing too world-shattering here. As another example, we've got this function x cubed minus 3x squared plus 3x. We're going to take the derivative of this thing. When we do, we're going to be like, yeah, we can simplify this a little bit to get 3 times the quantity x minus 1 squared. Well, this thing's only going to be 0 whenever x is equal to 1, right? So that's going to be our one and only critical number here. We're going to break up our interval from -infinity to 1, 1 to infinity. Choose test points and apply our test. Notice we have increasing, increasing. It's not always going to be the case that you're going to have an alternation between increasing and decreasing, right? You're not always going to alternate between the two. Sometimes you can be increasing, kind of level out, and then increase some more. This is actually, for whatever it's worth, one of the things when scientists are trying to model things like COVID and how it moves through the population, these are some of the same methods that they apply to those analyses. They'll be looking at incremental changes in the test positive rates or in the hospitalization rates, and they'll use that as a way of working out what the function, the model should be. So, a little bit more involved example. In this case, imagine yourself as a Ferengi, if you'll allow the Star Trek reference. You want to know at what point are you going to optimize your profits? Well, profit is defined as a function of revenue minus cost, right? Each of those have their own functions. So we're just going to take the difference of these two. Simplify it. Now we have our profit function. We're going to take the derivative, set it equal to 0. We're going to find that our critical number here is 300 games. My mistake, 3,000. 3,000 games. So from here, what we need to know is this going to be a high point or a low point, right? So we want to do apply the test to check to see if on the left we're increasing and on the right we're decreasing, because that would be a max, right? Concept check. Again, as I usually ask, I'd like y'all to check that out. All right. Relative max, relative mins. A relative max and a relative min is this idea of exactly what it sounds like. If you look at a function, let me actually draw an example function to point to. All right, as an example, this function here has one relative max and one relative min. Relative max, relative min. One way to think of this is, notice if we were to jiggle this function, and I literally mean just jiggle it, right? Excuse me. What we're going to find is that anything to the left or to the right of this point is going to be less than what's at that point. Similarly, down here, anything to the left or to the right of this point is going to be greater than what's at this point. So this must be a relative max, this must be a relative min. Because relative to the function values around it, it's maximum or it's minimum. One way of identifying this is by identifying the patterns that occur within our function. We're increasing and we're decreasing. So we know this has to be a max of some sort. We're decreasing and then we're increasing. So we know this has to be a min of some sort. So step one to finding this is to apply the derivative, set it equal to 0, and find your critical numbers. Critical number, right? In this case, we're going to have an undefined critical number because it's a cusp. Before I go any further, I do want to point out one failed case. All right. So in this example, what we've got is the graph of 1 over x. We're going to have a critical point at 0, right? We're not going to have a relative max or min at 0. Make sense what I mean? So we're going to have to do some testing with this, right? It's not going to be as simple as going through, finding our critical number. You're like, haha, this is either a max or a min. No, you're going to have to do some work. If your function is not defined there, you don't have a max or a min. So what this test really is going to be is to say, all right, within an interval, A to B, if to the left of C we're negative, and to the right of C we're positive, then we're going to have a relative min, right? But let's think about that. What we just described, just talking about the derivative itself, well, as we're decreasing, right? So if the derivative then changes and is now positive, we're increasing. So just looking at it this way, we can see this has to be a min, right? And if we flip the case, we're going to get that it has to be a max. But if they stay the same, we can't make a conclusion either way. So as an example of that, let's consider a graph we just saw a few minutes ago. This wouldn't have a relative min or a relative max, right? We're going to be increasing, 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 0, increasing, 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 right? As a couple examples of these, we have the relative min, relative max, and then the inconclusive forms, right? Really shouldn't call them inconclusive as much as just neither. All right, so let's consider this example. Here we've got a function is equal to x cubed minus 3x squared minus 36x plus 14. the derivative of this is going to be 6x squared minus 6x plus, or minus 36 . Well, notice we can pull out a 6 here, right? We're going to get x squared minus x minus 6. This is going to be factorable, right? Factor this as 6 times the quantity x minus 3 times x plus 2, right? Which is what we do here, factor it out. So now we can set our derivative equal to 0. When we do, we're going to find that our critical numbers are 3 and negative 2, right? So now we can break our intervals up into 3 different parts. Yeah. This is going to be negative 2. This is going to be 3. So here, this is going to be all x values less than negative 2. All x values between negative 2 and 3. And all x values greater than 3. Yep. So we're going to choose some test points through here. Let's choose negative 3. Let's choose 0. Let's choose 4. We plug in negative 3 into all of this. We're going to get 6 times negative 6, so negative 36, times negative 1. So f of x primed at 3 is going to come out to be negative 36 times negative 1, or just 36, right? At 0, we're going to have 6 times negative 3 times 2. 6 times negative 3 is going to be 18. Negative 18 times 2 is going to be negative 36. And at 4, we're going to have 1, 6, so 6 times 6, 36, times that 1, it's going to remain 36. So what we found then is that our function is increasing, decreasing, increasing, right? Having said that, we can conclude from this that this must be a relative max, this must be a relative min, right? And looking at what we've got over here, We're increasing up to a relative max, decreasing up to a relative min, and then increasing again. Everybody get that? People at home, excuse me, people at home, what do y'all think? Can y'all hear me? I'm docking off points for every unanswered question.
Yeah, we hear you.
Awesome. Awesome. I thought that might get y'all's attention. All right. How is this making sense to everybody so far? What do we think? Yeah? It's really just applying some analysis to figure out what the geometry of our graphs are going to look like, right? And naturally, if we go from increasing to decreasing, we can assume we're going to have a relative max. If we go from decreasing to increasing, we can assume we're going to have a relative min. This makes intuitive sense. Now notice what this lets us do without going through and actually knowing what the graph of our original function looks like. What this allows us to do is say, all right, I'm going to break out my number line to 3 parts. -2 to 3. That was a 3. Here, I'm going to be increasing. Here, I'm going to be decreasing. Here, I'm going to be increasing, right? So I know then my function is likely to look something like this. We're decreasing through here. We're increasing. We're increasing, right? Let's just do something like this. Well, that's kind of like the graph of our function up to a constant, right? Now all we have to do is move our graph up and down till we figure out which graph we're at, right? So knowing now just one solution of our function, let's just say we know the graph looks something like this. Now let's pin it to a point. Does this make sense what I mean? Yeah? So in this case, we could say, all right, at -2, our thing comes out to be what exactly, right? We could go through and be like, all right, this function at -2 is whatever. Pull this point up to that point, and everything else holds. So this is a method of not just figuring out information in reverse, like from data or whatever, but also figuring out what our graphs are going to look like without having to go through and calculate our function at a bunch of different points, right? Now we can say, what's our function going to look like at one point? We know generally that it's going to be increasing, decreasing. We can work with that now. Now, having said that, it is 9:20, so I will let y'all go. If y'all have any questions, I'll stick around. Yeah, have a good one, everyone. Is it already posted? No, not yet. Quite honestly, I had totally forgotten about it.
I don't know, I just like something hit me. I was like, wait, did I already miss it?
No, not yet. Not yet.
it doesn't feel like Wednesday because we didn't have class Monday, so I was like, what is today again?
I was too this morning, actually. When I first woke up, I was like, what is today? What is life even?
Yeah.
Folks at home, did y'all have any questions?
Have a good day.
I'm gonna take that to be a no.